Hello everyone, and welcome to today's webinar on surface analysis. My name is Rena Samsu, Marketing Manager at Eurofins EAG Laboratories. We have two of our principal scientists presenting to you today, Jim Gibson and Sasha Rodyansky. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Our question moderator, Laurie Lavanier, one of our surface science managers, will be answering some of the questions during the presentation. We will also collect these and address them during the Q&A session at the end of today's talk. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our first presenter, Jim Gibson, Principal Scientist in TOF-SIMS.
Yes, thank you and welcome. Today's webinar is Surface Analysis, TOF-SIMS, XPS, and Auger. Just first a little bit about myself. I've been doing TOF-SIMS for 15 years here at EAG and have about 30 years of surface analysis techniques. Quite a bit of that spent in the analytical lab at British Petroleum Standard Oil of Ohio. My training is in analytical chemistry from right here at the University of Minnesota. Our company, EAG, has over 600 highly educated employees. We're in 20 locations, serving 4,000 clients in 50 countries. Our parent company is Eurofins Scientific, a multi-billion-dollar global leader in scientific services with over 900 laboratories. Today's agenda will include an introduction to the SMART chart, a depth of analysis chart, talk a little bit about TOF-SIMS, the technique itself, and then I'll cover 4 case studies: mold release contamination on polystyrene, additive manufacturing metal powder ion imaging, pharmaceutical drug bead cross-sectioning, and then depth profiling of thin organic films on cell phone screen protectors. For the XPS, the case studies will be identification of a contaminant particle on PET, analysis of a stainless steel stent, pigmented contact lens study, and for the Auger, the case studies are stainless steel corrosion study and a nitinol defect characterization. At the soul of EAG is something called a SMART chart. It's an attempt to show the capability of all the techniques we offer. On the horizontal axis is simply the analysis size. So we range from centimeter sizes down to actually sub-nanometer in size. On the vertical axis are detection limits, atoms per cc on the left, and ranging from 100% atomic to part per trillion levels on the right. On the right side of the chart are the techniques that are more bulk technique, like GCMS. So they really have no effective spot size. And on the bottom are techniques that are more imaging. And there's also a color code. So for example, the blue techniques can provide elemental information. The red techniques, chemical and compound information. And then there's quite a few other colors here, including purple, which provides electrical information. All this can be found in a website with this chart in an interactive mode, so that's nice. Another useful chart shows the depth of analysis of each technique. So for example, TOF-SIMS has a very shallow analysis depth, only about a nanometer, 10 angstroms. Auger and XPS are also very shallow, about 10 nanometers. And these are up to 1,000 times shallower than some more routinely used techniques such as FTIR, SEM EDS, or Raman. And what this does for you is it allows you to catch materials or contaminants in a very thin layer that you might miss with more standard techniques. The chart also shows some of these techniques have arrows extending deeper, and this tells you that these deeper depths are available through sputter depth profiling, and that's just simply removing sample material with an ion beam. TOF-SIMS stands for time of flight secondary ion mass spectrometry. It's often referred to as just TOF. It's about $1 million piece of equipment. We have 4 of them in our network, 2 in California, 1 in the Netherlands, and 1 right here in Chanhassen, Minnesota. First thing to notice about TOF-SIMS on the bubble chart or the smart chart is that it's red. So not only does TOF-SIMS tell you there's sulfur on the surface of your sample, but it's in the form of dodecylbenzene sulfonate, a detergent. TOF-SIMS can have fairly small analysis spot size, micron level, and in certain cases, detection limits can be quite low, part per billion. It's a great technique for analyzing small, thin, and trace organics. Some of the key applications for TOF-SIMS are surface characterization of both organics and elemental materials. It's quite easy to survey a sample for everything that's present. We do a lot of mapping. Dozens of maps can be generated in just a few minutes. We can not only identify elemental and molecular species, but since it's a mass spec technique, we can analyze for a specific isotope of an element. We do a lot of failure analysis, failed adhesion, contamination, or delaminating coatings or blistering coatings. A lot of quality assurance and quality control in regard to evaluation of cleaning processes, and then just simply identifications of stains, discolorations, and hazes. The basic principle of TOF-SIMS is the sample is held at a high voltage. The primary beam is accelerated to the sample, and this causes sample ions to be ejected and then accelerated into a drift zone and detected. The lighter, all of the ions have the same energy, so the lighter ions will actually have a higher velocity and get to the detector first, hydrogen. Heavier ions such as iron will get there last, and then the large organic species and fragments will get there much later. And what we do is we measure these flight times very precisely, so we get a measurement of mass, a very accurate measurement of mass to mass resolutions of about 10,000. And the result is mass spectra. These are mass spectra of a polymer, polyethylene terephthalate. The top spectrum is a positive ion spectrum, and the bottom spectrum is a negative ion spectrum. On the horizontal axis is mass. On the vertical axis is simply intensity in counts. And what we notice is major peaks appearing for the compound. So the polyethylene terephthalate gives us a peak at 104, which is the fragment between the 2 green bars, an aromatic ring and a carbonyl. There's also another major peak at 149, which would be between these two yellow bars, aromatic ring, carbonyl, carboxylate. And then the 193 is also useful because that is the entire monomer unit. And then the negative ions, we get a major peak at 121, which is the aromatic ring and a carboxylate. And then the 76 is the aromatic ring itself. These peaks can be characteristic of the compound, and we'll match them to libraries to identify them. Or if it's not in our library, often customers will submit a reference material from their process, and we can match it to that. Here's a picture of the 3 instruments that we have in the US. The top right instrument is the one we have here in Minnesota. It's called the TRIF3. It's made by Physical Electronics, also in Minnesota. It uses a gold ion beam and a TRIF analyzer. The TRIF analyzer is really nice for samples that have topography to them. And I might also point out it has a cold stage. That's what this doer is for. So samples that are not quite solids we can freeze, or samples that might have a volatile contamination, we can lock it down by cooling it and are able to analyze it and identify it. The 2 instruments we have in California are Auger TOF-5s. One of them both of them actually use bismuth primary beams and a reflectron analyzer. But one of them actually has a argon cluster beam used for depth profiling organics. And the other one has a very large sample entry stage for analyzing large wafers. It's used a lot for semiconductor analysis. The first application of TOF-SIMS is of mold release contamination on polystyrene. A common use of TOF-SIMS is comparing contamination on sets of similar samples, or just simply good and bad samples. In this sample, silicone-based mold release contamination was compared between polystyrene parts. The top spectrum is of the clean polystyrene part, so all it is showing is aromatic ring fragments, the largest being here at mass 91, C7H7. The bottom spectrum shows a peak at 28, which is silicon, and then some methylated silicon peaks, and then out here at 147, a siloxane peak. And these are characteristic peaks of polydimethylsiloxane, and in fact, there's so much contamination here on this part that you don't see any of the polystyrene. It's being masked. The center 2 spectrum are just different levels or different degrees of contamination. And what we'll often do is we'll integrate the pertinent peaks, normalize them, and then tabulate them and include that in the report, and it makes it really easy to compare sample sets. In the second application, we move from samples requiring only spectral data to those needing mapping. In this example, we analyze a series of metal powders that are used in additive manufacturing. In the manufacturing, an E-beam or laser beam is scanned across the metal powder, causing it to solidify and forming a part. This type of manufacturing allows for complex geometry, compositional gradient control, lightweight structure design. And as you can imagine, in this type of manufacturing, the surface of the particles or the surface chemistry of the particles can be very important, and TOF-SIMS can measure that. We looked at 3 different powders. One was composed of titanium, aluminum, vanadium, one nickel titanium, and one was just an aluminum powder. And as you'd expect, we see the main components. We see at 27, aluminum. We see the titanium at 48, and we see the vanadium at 51. But we also see things we didn't expect. Lithium, boron, calcium, iron, and a pretty strong signal for copper. In addition, we pick up the organics. We detected phthalates and detergents on these samples also. We went on to generate images, and these is a set of images we generated for the titanium, aluminum, vanadium powder. The aluminum is in red, the titanium is in green, and the unexpected copper we put in blue. And as you can see in these images, the individual particles have pretty uniform distributions. But when you overlay the images, you can see the particle-to-particle chemistry changes pretty dramatically. For example, this little particle number 6 is really green compared to the rest, so the surface level of titanium is much higher than the other particles. Some of the particles are a little more red, like number 8 here, so it has a little higher aluminum level. And the particle 4 and 5 have more of a bluish hue, having the unintended copper on their surface. We can go into an image like this and extract the composition out of each particle or the particles of interest, and then we can do that retrospectively after the data is taken. And then we can plot it. And this plot on the right is just showing you the spread of elemental concentration on these particles, and there's a dramatic spread. We like to highlight the surface analysis capabilities of these techniques, but they're not limited to just the surface. Cross-sectioning samples allows for compositional measurements of the bulk. 2D chemical imaging of finished drug products can be invaluable for understanding the location and distribution of organic and inorganic constituents. We often do this with SEM or EDS Raman mapping. They're very complementary techniques. This kind of data aids the formulation chemist to better design the drug, and the information can be critical to intellectual property cases where patents often strictly define the location and function of the compounds. And I might add that 3D imaging is also possible, but it does add a layer of complexity to the data and the data acquisition. In this application, we took a drug bead from a heartburn medicine and we cross-sectioned it. The bead had the drug, the active pharmaceutical ingredient, which was lansoprazole, which has a formula like this and a chemical structure like this. Has lots of nice functional groups that'll ionize for the TOF-SIMS. The bead also included many excipients, and these are compounds in the bead extra in addition to the drug. An optical image of the drug bead, of the cross-sectioned drug bead, shows a shell structure, a core, and you can see it's really quite non-homogeneous. We took TOF-SIMS data from this red box, which is 250 microns square, and generated TOF-SIMS images. And these were quite interesting. Initially, the total line image is just an image showing from all of the signal we acquire. And then we generated 3 elemental images, magnesium, silicon, and titanium. And we can see the magnesium and silicon are concentrated in the shell, and this is implying talc, the presence of talc. The titanium is also in the shell, and that shows us the location of titanium oxide. And then in the magnesium image, we also see magnesium present in little spheres in the core of the bead, and these turn out to be magnesium carbonate. We also are able to get the organic component of the bead, and the central image shows the distribution of polyethylene glycol, hydroxypropylcellulose, sucrose, and then lastly, the drug, the lansoprazole. And I've included two images for the lansoprazole. The bottom right one is actually the entire molecule ionized, and that's really nice if you can get that. It's not always available. But the most intense image was this one here at 205, which is the second half of the molecule. Color overlays help to register distributions. The magnesium in red, the lansoprazole in green, and the sucrose in blue can be seen to be complementary to each other in the cover overlay. And the last application illustrates how the near surface of a sample can be accessed by depth profiling. Cell phone screen protectors are generally made out of plastic with a thin oleophobic coating to prevent fingerprints. 2 cell phone screen protectors were analyzed, a new one in blue and an aged one in red. And we generated a depth profile with our argon cluster beam going from the surface of the sample, 0, to a depth of 40 nanometers. So still pretty shallow. And what we found was the oleophobic coating had several components to it, a fluorocarbon component, which we tracked by the C2F5 ion, and that's shown in a dotted line. We also saw a fluoroether, the C2F5O, which we show in a dashed line. Keep doing that, sorry. And the solid line is the silicon from the underlying screen protector. So what we see is the new screen protector has a much thicker fluorocarbon coating, about 14 nanometers than the aged. And we also see that the fluoroether is lower on the surface of the aged and dissipates faster into the bulk. This type of depth profile used to be restricted to just inorganics and primarily semiconductor materials, but now with these new cluster beams, we can do this kind of analysis on organics. So in summary, TOF-SIMS can analyze both elemental and molecular information, and it can do it on very thin contamination layers. It's quite easy to survey a sample for everything present. We can measure species to very low levels, part per million levels. Spot sizes can be quite small, and mapping is quite easy. And we can analyze insulators and conductors. Some of the limitations are the organic information can be limited, so not all species give the same amount of signal. The samples have to be vacuum compatible. However, we can freeze samples that are not quite solids. And at times it's too surface sensitive. And what this is referring to is if you have a feature of interest and then somebody handles it or throws it in a bag that's full of plastic slip agent, and then we try to analyze it, all we'll see is the contamination on top of your feature of interest. And that is often an issue. So that's the end of the TOF-SIMS part of the webinar, and I'm now going to hand it over to Sasha Rodnyansky to tell you about the XPS.
Hello, my name is Sasha Rodnyansky. I have about 35 years experience in different surface analysis techniques, and specifically in XPS, about 25 years. So we're going to start with, sorry. Let's get, for some reason it's, I apologize. Okay, so we're going to start this first part of my presentation will be about XPS, and which stands for X-ray photoelectron spectroscopy. There is another term for this technique, electron spectroscopy for chemical analysis, with acronym ESCA, and basically they're used interchangeably, but XPS reflects on physical side of the technique and ESCA more on the application side. As you already seen the smart chart, XPS occupies the top section closer to the right, and it's still pretty substantial size bubble, showing that the spot size could be from almost 10 micron to more than a millimeter, and the detection limits are from 100% to about 0.1 atomic percent. The XPS technique is based on photoelectric effect. So X-ray beam falls onto the surface and generates photoelectrons as far as it can reach, and it can go down for several microns, but only those photoelectrons generated in the top 100 angstroms or even less can go out of the sample and be detected by the spectrometer. In XPS, we measure kinetic energy of those photoelectrons ejected from the sample, but normally we plot signal against binding energy, which is this information obtained by using this simple formula. And conversion to the binding energy scale allows for identifying elements and their binding states for many elements, and also it provides consistency in data when using different X-ray sources. Key applications of XPS include characterizations of stains and discolorations. We can do compositional analysis of powders and residues. We normally often evaluate cleaning processes. We can determine oxidation state and other chemical states of different elements. Like I mentioned before, we analyze carbon functionality. So polymers are often the samples that we analyze, as well as low-key dielectrics. Like in TOF-SIMS, we can do depth profile using ion beams to analyze thin films and stack of film films. The first example is this contamination particle on the surface of PET, polyethylene terephthalate. The particle is pretty small, and we had to use 20 micron diameter X-ray beam, and we analyzed two locations on the particle itself and also outside of the particle as a control, area 2. As you can see in the survey spectra on the right-hand side of the slide, the control surface has two main peaks, which are carbon and oxygen, and trace levels of silicon, which is a contaminant. Carbon and oxygen are components of PET. The top survey in red is dominated by fluorine. The next slide shows high resolution carbon 1s spectra. And again, the spectrum from control area is typical for PET It's dominated by hydrocarbon and has weaker CO and ester functional groups, while the spectrum from the particle has two peaks of similar intensity, one of which is CF2. So from that, we can conclude that the majority of contamination in this particle is fluorocarbons. This example talks about the analysis of stainless steel stents. And the location of the analysis is shown in the image on the left. The survey spectrum on the right was taken from that spot. And as you can see, there are elements detected that are listed. The most abundant elements are carbon and oxygen, and then alloy elements, chrome and iron. As well as there are some smaller components of the alloy and some contaminants at low to trace levels. This slide from the same spot contains high-resolution spectra from 4 most abundant elements. And it's important to notice that chrome and iron, the alloy components, are present in 2 chemical states, metallic and oxidized. On the right of this slide, we see a sputter depth profile, which was obtained using argon ion beam. And we know from this profile that the surface of the stent is enriched with chromium oxide, which is a passivation layer. And the thickness of this passivation oxide layer is about 30 angstroms, as we can determine based on known sputter rate. This example is talking about pigmented contact lens. In recent years, many manufacturers started making those, and there is one interesting question important for both manufacturers and consumers, that sometimes pigments may be segregated to the very surface, and they may cause irritation of the eye. So we would like to have them not on the surface. And this lens was purchased, and we analyzed the area right above one of those brown spots. And this is a survey scan from that location. As you can see, there are carbon, oxygen, some low level of nitrogen and silicon, but no indication of pigment specific species. This slide shows sputter depth profile. And unlike the earlier shown sputter depth profile in the stent, this one was obtained using a C60 sputter beam, buckyballs, which is good for depth profiling of many different polymers. And you can see here that the pigments, which were iron oxide and titanium oxide, indeed are buried. And they started showing up a little bit deeper in the profile, and iron oxide is much more abundant than titanium oxide. The strengths of XPS techniques include that it's capable of elemental identifications of essentially almost all elements except hydrogen and helium. It can determine chemical states, oxidation states. The analysis is quantitative, and it can analyze both conductive and insulating materials. Limitations are the following. The detection limits are typically about 500 ppm. The spot size, smallest spot size, about 10 micron, and there are limited organic information. We can often determine functional groups, but not specific compounds. And again, it's a UHV technique. But like with TOF-SIMS, on some of the instruments we have a cold stage capabilities where we can freeze some liquids or freeze materials which have volatile components on the surface to preserve them and analyze. And contact lens, by the way, one of the typical sample which we often use cold stage applications. The following two techniques discussed in our webinar today are Auger and TOF-SIMS, and if the location feature area is too small for XPS, oftentimes we can use Auger, and if we need more organic information, we can apply TOF-SIMS. So these techniques are often used in combination. Now we're going to talk a little bit about Auger electron spectroscopy. Again, on the bubble chart, on the smart chart, you can see that Auger takes a pretty wide span on the top of the chart. So its detection limits are similar to those of XPS, but the spot size is has much broader range. Again, it's from about 1 millimeter and down to almost 10 nanometers. Sorry. The Auger process involves several particles, and specifically there are, in addition to the incident beam, which is in our case is incident electron, there are 3 other electrons. So we have incident beam kicks out a secondary electron, and which creates a hole in atom. So in other words, it's an excited ion. Then another electron can fall into this hole from a higher orbital, high energy orbital, and there are 2 options how this energy, extra energy, can be dissipated. It could be one relaxation process as shown here is X-ray fluorescence, when this energy is given to X-ray photon, or it could be given to another electron, which is called Auger electron. And these Auger electrons are the subject of our this portion of our presentation. Like XPS, Auger electron spectroscopy, it has about the same depth of analysis, and it's much better than that of SEM. In addition, its energy resolution, its spatial resolution, I'm sorry, is much better than XPS. The following key applications typical for Auger analysis. We oftentimes analyze particles and small features, and the particles may be as small as 25 or even less for some instruments, 25 nanometers or even less. We can analyze submonolar, which the films would be too thin for ADS, and thin film analysis, again, including some stacks of films, could be analyzed using depth profiling. The analysis is semi-quantitative, and it could be quantitative with standards. The first example includes the analysis of corrosion spots on stainless steel part. In the SEM image on the left of the slide, you see 3 locations were selected, and the survey scans, red, blue, and cyan, were obtained from those locations. The survey scans, in addition to varying chrome and iron ratios, they also show some sodium and calcium contamination. This slide shows Auger maps, and the calcium map on the bottom right is showing very bright spot, and this spot corresponds to location. To location number 1. This biggest particle here, that's corresponds to calcium. So we know that calcium and as well as sodium could be precursors of corrosion, and so these locations were specifically chosen as potential corrosion spots or future corrosion spots. This slide shows a dendrite looking defect on the nitinol part, nickel titanium, and we zoomed in a smaller section of this defect in this SEM image on the left, and also set up 3 points in different locations, 2 on the defect and 1, number 3, outside of defect. And as you can see, the 2 surveys, red and blue, which were obtained on defect, show substantial levels of sodium, and very little sodium is found in location 3, which is more clean, smooth location of on the part. Here, this SEM image of dendrite is compared to the sodium Auger map, and you can see that the almost entire defect is covered with sodium. Auger electron spectroscopy has following strengths. It's very surface sensitive. It has very good depth resolution and very good spatial spot resolution. However, of course, it has some limitations, and the best quantification requires standards. It's very difficult to analyze insulators with Auger. For that, you need XPS or TOF-SIMS. And the samples, again, must be vacuum compatible. So why choose Eurofins EAG laboratories? There are several bullet points why the client may decide to choose our services. Client confidentiality is core to our business, and we have multiple accreditations, like ISO 9001 and 17025. We own many instruments, more than 2,500 instruments worldwide, and we can oftentimes decide customized analysis using multidisciplinary approach and multiple techniques. At this point, I would like to thank you.